Okay, we're looking at continuous probability distribution functions. We looked at binomial, discrete, continuous, and we talked a little bit about discrete continuous in previous videos, but discrete numbers, if you remember, they're basically numbers that are finite. So for example, you get a test score of 7.5 out of 10, or you have 3 members in your family. They're all discrete numbers. They don't have to be whole numbers, but they have to basically finish. They have to be finite. Continuous numbers are an example of numbers that just continue on forever. For example, if I were to say, what's the time at the moment? We'd say it's 12 o'clock, but it's actually not 12 o'clock because depending on how accurate your watch is, you'd say it's 12 o'clock and 10 minutes and 25 seconds, and then you can continue on actually measuring time to infinity, really, depending on what sort of tool you've got. So that's an example of a continuous variable. So when we're looking at continuous variables, we could never really say, in theory, we could never really say what's the probability of the time being 12 o'clock, because really 12 o'clock doesn't really happen. There's always going to be a time either side of 12 o'clock, depending on the tool you're measuring. So when we're talking about continuous probability and we're looking at the probability of something happening, we kind of treat equals and less than and equal and greater than as the same, because you can never really get an exact continuous number. But we'll see that you'll see that when you do some examples. Let's have a look at continuous probability and an example. Now, with continuous probability, the way we work out probability is we actually map the distribution. So previously we mapped the distribution by drawing tables of all the different outcomes. Now, if you think of continuous variables, basically you can't say what's the probability of getting 3 heads or 4 heads, because in continuous variables there's all the little numbers in between as well. So because it's continuous, we need a probability for every single thing that can happen in between those numbers. And the only way we can represent that is via graphs, because a continuous graph, like the one up here, can show every single occurrence of every number between 5 and 11 and what the probability is. So for continuous probability, we are going to be using graphs to answer these questions. And so for this particular example, we've got a function here. Here is the equation, and here is the graph that represents this equation. This equation says that this function exists between x between 5 and 11 only. Outside of 5 and 11, the probability is equal to 0. Okay, so think of this graph as representing probability. I'm going to draw 0 as well on this graph. So if we said, what's the probability of getting a 12 for this particular example? A 12 would be a probability of 0. What would be the probability of getting, say, a number in between 5 and 11? Quite high. So this graph represents the probabilities. Okay, so where do we go through from here? So basically there's a basic rule, and it takes us back to integral calculus. So another application of integral calculus, area under the curve. The area under the curve actually tells us the probability of something happening. So a very important rule that we can recognise is that when we draw all the area under this curve, we know that all probability must equal 1. So the first thing is that if we take the area between 5 and 11 for this particular function, it must equal 1. So if we find the area between 5 and 11, it must equal 1. If it doesn't equal 1, then this is not a probability, this is not a continuous probability distribution function. So that might come up on the exam. It might say, prove that something is a continuous function, and then you have to prove that the area under the curve actually equals 1. If you want to have a go, type that in, between 5 and 1, work out the area, has to equal 1, and you'll see it does. Okay, so let's look at a question. What is the probability of getting less than 7? Okay, so 7, say it's about here, there's 7, probability of less than 7. So I'm going to colour all that in. The probability, this basically represents the probability of getting less than 7. So it's basically less than a half, okay? I'm looking at how much area is covered in. Remember, all of that is equal to 1. So it's going to be, I don't know, around 0.3 or something. We'll take a bit of a guess. But we actually calculate it, yeah, using this formula. The rule is that to find the probability between two numbers, we find the area under the curve. So for this example, we want probability of x being less than 7. So it's equal to the bottom terminal, the lower terminal. So this distribution only exists to 5. So that's the lower terminal is 5. The upper terminal, because we're looking for x less than 7, the upper terminal is going to be 7. So we're finding the area between 5 and 7. So 7 of the function fx dx. Okay, do it by hand, calculate it by hand, or plug it into the calculator. We all know how to do that on the calculator now. And for this particular example, I've got the answer here, 0.26 or 26%. Probability of getting less than 7 is 26%. You may find also some examples where the graph is, say, for example, a exponential, something like that. Okay, and that basically goes to infinity. So if, for example, we're saying what's the probability of being x greater than 2, okay, we'd write that as 2 to infinity, fx dx. Okay, so that's continuous probability distribution. Again, very simple. We need to also talk about measures of centre and spread, which we'll do in the next video.